So I did two things, and those two things came from different areas. And the role of mathematics in both stories is to identify the common patterns, right? And the common patterns are that in both problems we have to compute, well, we have to deal with exactly the same thing, right? And that's where mathematics comes in, and we say that this is going to be an important quantity. The limit as delta x goes to 0 of the sums from 1 to n of f of xi times delta x. So that's important, right? Why? Well, because we saw it already twice in different areas, and we will see it a couple of dozens times during the rest of semester, repeating all kind of different things about physics, about mechanics. So we will have to deal with this, and at this point all we do is we give it notation. So this thing that you used to see is just a notation, right? We say it's an integral from a to b of f of x dx. And we say that this is a definite integral. So we introduce terminology so that we don't have to talk about area all the time or velocity all the time, right? So the problem about area in the context of velocity is that it will be hard to explain to a physicist that the distance to compute is equal to the area. Area of what? And why would you think about area, right? So instead of bringing geometry to physics or physics to geometry, we would create one thing, one concept, right? Call it definite integral, and we will use it in all the applications. Now, what makes this not just one symbol, like one hieroglyph, right? One of those millions that exist. What makes it better than just one symbol is your ability to operate with this symbol, your ability to manipulate with it. So what we had in both examples for area and for the velocity, what we had was the expectations that, for example, additivity happens, right? So once we forget about those applications and we give mathematical definition, well, we have to add some properties to it so that we still have some intuition about how this behaves. So, for example, what can you say about integral from a to a f of x dx? So you expect it to be 0, but why? And now, you see, at this point, you may want to rely on one of the examples, right? Saying that if you think about the area, then area over one point is definitely 0, and that's why this is 0. Or the distance traveled over the time interval of length 0 is definitely 0, right? So you might want to rely on to those examples that you know. But a better way would be just to list those properties and have those properties, and fortunately we don't have many of them. So this is a triviality property. And now what would be additivity property? How would you? So let's say what additivity is in terms of the area, and then try to mimic here in the formula what we want. So if you have to compute this area, how is it that you want to cut it? Well, we only cut vertically, right? So it makes sense to cut it like this, and then to say that area of this left piece plus area of the right piece equals the area of the whole piece. Right? So we call this A, B, and C, and then this picture suggests what kind of additivity to expect from the integral. Integral from A to B of the function f plus integral from B to C of the function f is equal to the integral from A to C of the function f. So that's how you convert property from there to here, and that's exactly what makes this symbol functional. Right? Now, if you know this property, you don't have to go back to your favorite example and check, is it indeed that some of these two integrals equal to the third integral. You just use this property, and there are consequences. And the consequence of this is going to be something that you would never think about geometrically. And it's called corollary of this property. Because now, if I look at this property, and by looking at this property, I forget about either area or velocity, I look at this property abstractly, right? So this is some number plus another number equals another number. What are A, B, C? A, B, C are also numbers, right? Now, what if I make C equal to A in this formula? Because now I'm just playing with the formula, right? So what if I make C equals to A? What I have is from A to B plus from B to A equals from A to A, and I know from A to A is 0, right? So the consequence of that is sum of these two is equal to 0, and therefore one of them is equal to minus the other one. So we conclude the integral from A to B equals an integral from B to A with negative sign. But this is not a conclusion coming from geometry, right? It says that this positive area has to be negative of something, and that something must be negative then. And geometrically, we never think about area as negative value, right? So what it means is that this abstraction and our attempt to play with this abstraction, make it functional, make it work for whatever numbers I want, right? And that's exactly what makes mathematics work. If you have a formula, you don't have to think about which numbers are going to be usable in the formula, which numbers are not going to be usable. If you want to expand the square, you just expand it without thinking of what the terms are. So if you want to use any number, well, you have this consequence. And the consequence sometimes projects back into application. Sometimes it doesn't. For the area, it makes practically no sense. Why would you think about negative area? Does it make sense for physics? What does this mean in physics? Does it mean anything? Well, it doesn't mean much, because if we assume A is less than B, this means distance traveled as time went from A to B, and that means distance traveled as time went from B to A. And doesn't make much sense, right? For some other applications, this will make sense, but not for these two. So we will stay with those properties, and we will treat them as just nice features of the formulas. And sometimes they will make sense in application, sometimes they will not. But these are exactly the features that will make formulas work, regardless of the numbers involved. What else? Oh, linearity, the loss property. Now, this property is about, let me write it down on this board. It has two pieces. First claim is that if you have an integral from a to b of the sum of two functions, then it is equal to the sum of the integrals. Why is that? Well, because if you look at the definition, and instead of f, you have f plus g, you can always multiply through by delta x and separate those f times delta x plus g times delta x. It's basic distributivity property that promotes itself through summation and through limit. And you get this nice feature, but the heart of it is distributivity of multiplication with respect to addition. Now, this can hardly be seen geometrically. And that's exactly what brings the power to computations. We can easily compute using this linearity, and we can hardly see it geometrically. The last thing is integral from a to b of a constant times f of x. And that is exactly equal to the constant times integral from a to b f of x dx. And again, the reason for that is that if you multiply by a constant each term here, you can factor this constant out of the sum. And when you compute the limit, you can factor the constant out of the limit. So again, this is very simple algebraic property, but you can try to plot a graph of a function multiplied by a constant and see why the one area is constant times that area. It's not easy to see. So these are all the properties that we will ever need from definite integral, and we will have fundamental theorem of calculus to conclude the list of all possible properties that we will ever need. Okay, I think I will stop here for today.